Alright guys, this video is going to be talking about some additional proportionality theorems that we can use now that we've talked a little about similarity. And so the first one here is what we call the triangle proportionality theorem. And you may have seen some problems like this before. This is indirectly similar to our angle-angle similarity postulate that we talked about in the last lesson. Basically, in short, what this is this is telling us is that if a line is parallel to one side of a triangle and it intersects the other two sides, it always will divide those sides proportionally with each other. And so what I'm looking at over here in this drawing is it's basically saying that if I know that this line and TU, so QS and TU are parallel, what that's going to tell me is essentially TUR and QSR are going to be similar to each other. So it allows me to create this proportion, and we can be able to solve for missing sides of the shape here. On the reverse side of things, what we actually can also do is if we know that a line divides the two sides of a triangle proportionally, in reverse, hence the converse, we can say that it's going to be parallel to the third side. So in reverse, if we are able to find out if QT and RT, if they're in the same ratio as, let's change colors here, RU and US, then we know that these lines here, I'll color this in black here, then we know these lines have to be parallel to one another. So let's take a look at an example of where this would be applied here. And what it's giving us here in this first problem is that in the diagram, QS and UT are indeed parallel. So what that's already telling me right now is that this triangle, RQS, and this bigger triangle, RUT, those are actually going to be similar to each other. And the reason that is, going back to why, is that these angles are corresponding, these two angles are corresponding, so it makes them similar to each other by angle-angle. But moving back to the problem, they're telling us that RS is 4, ST is 6, and QU is 9. We need to find the length of RQ, so that's our missing X. So this new proportionality theorem basically tells me that I can take the top portion X and create it into a ratio with the bottom portion 9. And now I can say on the other side that 4, which is the top portion of the right side, is proportional to the bottom portion, which is 6. They're in the same ratio as one another. And so now I can cross multiply these. I'm going to get 36 equals 6x when I cross multiply. Divide both sides by 6, and my x value here ends up being 6. The question is asking us to find RQ. Well, RQ is indeed X. And so what I can write down to finish this question, RQ is equal to 6 here. Moment right now to pause this video and try guided practice problem 1 and guided practice problem 2. Once you've had a chance, press play and you will get a chance to check your answers. At this point, you should have checked or tried these problems out. So in number 1, what we're looking at here is we're going to compare 35 to 44. Those sides are proportional. And that's going to be equal to ZY, which is the corresponding side, X, and its 44's corresponding side, which is 56. I'm going to cross multiply these, and I'm going to get 1,260 equals 44x. Last but not least, we divide both sides by 44, and that gives me actually a decimal value, which is okay. We'll go ahead and I guess we'll round it to the nearest tenth. I get 28.6 as my answer. One thing to note about this before we move on to number 2 is that there are varied ways that you can set up your proportion. For example, someone may have set this up as 44 over 36 equals 35 over x. And that's okay as long as the sides are corresponding with one another. Now in number 2, we actually have all 4 portions of our triangle that are given to us. They gave us 90, 50, 72, and 40. What they're asking us to figure out here is if PS and QR are parallel to each other. And so all we're going to do is test this to make sure they come out with the same scale factor. 90 over 72 corresponds with 50 over 40 because they're top to bottom and top to bottom. And I can either take the cross products of this or I can divide them separately. I'm going to do the cross product. So 90 times 40 is going to be 3,600. And then when I do 72 times 50, I also end up with 3,600. Because these cross products are the same, determine if they're parallel, we're going to end up saying, yes, they are parallel. Moving on to the last part of this lesson, here are the last two theorems involving proportionality. So the very first one, there's something I'd like you to add here. It says if 3, and then I want you to add or more, because there could be more possibly in problems. 3 or more parallel lines intersect two transversals, then they divide the transversals proportionally. So as we look at this question, here's a drawing that is associated with this. So I have R, S, and T, and those are all parallel to each other. These are transversals, and recall that a transversal is merely just a line which intersects multiple lines. So these two transversals, which I've drawn in black, are actually going to be proportional to one another. What that means is, for example, that UW, which is this length here, and WY, or I should say VY across here, VX, those two are going to be in the same ratio as WY would be to XZ. We'll look at an example of how that's applied in just a moment. And the last part of this looks at a triangle with an angle bisector. So this red line that you see here is an angle bisector. If a ray bisects an angle of a triangle, which it is here, then it's going to divide the opposite side into segments whose lengths are proportional to the length of the other two sides. So what I'm meaning by that is if I take the length of AD and I divide it by the length of DB, I'm going to actually end up with the exact same ratio as if I took the side CA and I divided it by the side CB. Once again, we're going to see an example of Theorem 6.6 and Theorem 6.7 here in just a second. And that time is now. So let's look at example 3. So in example 3, it's giving us here angles 1, 2, and 3, which are all congruent. What that's going to tell me is, since I know they're all congruent, this and this and this are all corresponding angles. That means Main Street, 2nd Street, and South Main Street are all parallel to each other. They also told me that the length of GF, so that's from here to here, is 120. The length of DE is 150 as it's marked, and CD, which is marked here, is 300. What we need to find is we want the distance of HF. So that's this entire length here. Now we know FG is part of that, and that's 120. So really the only part I need to find is this value of X here. And so in order to do this, because we have multiple parallel lines and we have two transversals, our property, our new theorem that we just talked about, basically says that if I take the portions of the transversal, so 120 and 150, those two side lengths are going to be proportional in the same ratio as the X and the 300. And so what I'm going to do with that is we're going to write a proportion for this. So I'm going to take the 120, I'm going to write it in the same ratio as the 150, and we're going to set that equal to X over 300. So this allows me now to solve for this, and all we're going to end up doing here is cross multiplying to solve. So we take 120, multiply that by 100, and that's going to give us, it looks to be 36,000, hard value. 150 times X is 150X, and now we just finished solving this. Divide both sides by 150, and when I do that, that actually gives me a value of X here, be 240. Now that's not the answer to our question, because we actually needed to figure out the entire length of FH here. So to do that, I'm just going to find FH, taking 120 and adding 240 to it. So that's going to give me 360, which is what we're looking for. Last example is going to take a look at our third and our final proportionality theorem involving angle bisectors. And so right away, before we even start reading the problem here, they already told us that there's an angle bisector, and we see that in the drawing over here. We're going to use the given side lengths to find the length of RS. So I'll highlight that in green so we know what we're looking for. So basically, again, the theorem that we talked about on the previous page is saying that the angle bisector, which is RP here, is going to cut so that RQ and QP are going to be in the same ratio as RS, which is in blue here, and PS. So we can do that to set up a proportion. So let's go ahead and set that up now. So I'm going to switch back to my pen here. So I know X and 13 are in a ratio to each other. Oops, not 30. Let's go back and get rid of that if I can find my eraser. So it's going to be X and 13, perfect, is equal to, now here's becomes our problem. This yellow, we have nothing, we don't know. So I'm going to leave that blank. I know the corresponding to 13 is our 7. So the question is, what do we put inside this blank? Well, in order to do that, some people right away might say, let's put a y there. But there's a major problem with this. We now have an equation with two variables. We don't want that. We won't be able to solve that. So what I have to do is actually look at this side and recognize that this entire length is 15. So this whole length is 15. I've already called my RSX. RQ, I want to write that in terms of X. So the way I'm going to do that is give you a quick little analogy here. So let's pretend, once again, this whole thing is 15. Guys, so it's our triangle. And let's say that this part down here is 5. How do you get this top part? Well, last I checked, what I would do is 15 minus 5, and that would give me 10. Let me give you one more scenario so we can make this connection. So maybe instead of 5, let's say that that bottom length instead is, I don't know, 10. Well, to find this top one, we're once again going to do 15 minus 10, which gives me 5. So in general, whatever this bottom value is, you're always going to take the entire length and subtract the bottom value from it. So case in point, when we look at this yellow blank, we know that it's going to be 15 minus whatever this green segment is, which we know is called x. So I'm going to actually call this 15 minus x. And now we have something we're able to solve. So now we can begin our cross multiplying. We're going to get 7x equals, be careful here, you need to distribute this. So the 13 gets multiplied to the 15, which gives you 195. 13 times negative x is going to be, if I can write it correctly here, negative 13x. Now we're just going to do the algebra. So the algebra quickly, we're going to get 20x equals 195. And we're going to get our x value here, which I'm out of space. I'm going to write it over here. X is equal to 9.75. So that is indeed the length of our S. So I can actually, for my final answer, write RS equals 9.75, and we have our solution. So now that we've taken a look at these examples, let's take a look at guided practice 3 and 4. What I would like you to do now is to try both of these problems on your own. Pause the video now, press play, and I'll have solutions listed here. And here are the solutions I've come up with. I have to go over number 4 with you in a moment, but as we look at number 3 here, we know that 16 and 15 are going to be in the same ratio as x and 18 since these lines are parallel and the transversals cut through them. So I set up my ratio as 16 over 15 equals x over 18. Once again, that may not be the only possible way to set the proportion up, but this also works good enough. We cross multiply, we're going to get 288 equals 15x. Solving for this, we get 19.2, which is the length of AB. Going to number 4 now, I set up and I did some color coding. And once again, the left side of the bisector is going to be in the same ratio as the left side as the blue is corresponding to this blue. So I set my proportion up to look like this. Now, once again, we could cross multiply this, but I actually noticed something. Remember that these are equal proportions. Top number is 4, the bottom number is 4 root 2. If this is 4, what must this x value be? Well, it has to be the same because the numerator is the same, the denominator must match in order for this to work. So it ends up being 4 times the square root of 2. Now, had this not been the case, you still could have multiplied this. I would have had 4x equals 4 times 4 root 2 is actually going to give 16 root 2. We'll talk more about radicals in the future, about how you work with them. Divide both sides by 4. So x ends up just equaling the 4 root 2, which is what I started with. That concludes this video. There'll be some additional videos coming up on Canvas here with some help with your classwork.